Imagine a future where your robot companion isn't just, a pre-programmed machine, but something that can truly understand what you're saying, see its surroundings, and then actually act on your instructions. This isn't quite science fiction anymore. It's the really exciting frontier of vision language action models, or VLA models. But here's the current reality check. Building these intelligent robots often means using these absolutely massive, power-hungry models. And they need tons of pre-training on huge amounts of robotic data. Think big data centers, massive costs, slow development. It's a real bottleneck for anyone trying to innovate in robotics. So our deep dive today is all about a significant breakthrough, a new approach called VLA-Adapter, and it's designed specifically to tackle these problems. We're going to unpack how VLA-Adapter lowers the barrier to entry for advanced robotics, delivering really top-tier performance with surprisingly small models and much faster training. It makes a sophisticated tech far more accessible to you.
You've really hit the nail on the head there. The core goal of VLA models is, well, to let robots operate directly from natural language. So taking multimodal info, what it sees, what you tell it, and then aligning that smoothly with the actions it needs to take. It's about bridging perception and action efficiently.
Right, building that bridge.
Yeah.
And you mentioned current models rely on these huge vision language models, VLMs, pre-trained on massive data sets.
Yeah.
What specific hurdles does that create, practically speaking? It's not just the size, is it?
Oh, definitely not just the size. That's a big part, sure, but it affects everything down the line. These large VLMs lead to some pretty critical bottlenecks. For example, fine-tuning them takes forever. They also demand a huge amount of GPU memory. We're talking like 62 gigabytes of VRAM for just one 7 billion parameter model. That's serious hardware.
Wow, yeah.
And then there's inference efficiency, how fast the robot can process and decide. Current models might hit around, say, 71.4 hertz throughput.
Which sounds fast, but maybe not for complex real-time stuff.
Exactly. For intricate tasks, you need much more responsiveness. So all this leads to the big question. How do we bridge vision language to action more effectively, without these crushing resource demands?
And this is precisely where VLA-Adapter comes in, offering this novel bridging paradigm. It's designed to cut down the reliance on those big VLMs and all that pre-training. And what's really striking is that it gets top performance using a tiny backbone, only a 0.5 billion parameter model. That's, well, tiny compared to the usual suspects.
The efficiency gains are, frankly, remarkable. VLA-Adapter doesn't just reach state-of-the-art levels. It hits the fastest inference speed reported so far, 219.2 hertz throughput.
219.2 hertz. That's a massive leap.
It is. And think about what that means for you, the user or developer. You could potentially train a powerful VLA model in just 8 hours. And get this on a single consumer-grade GPU, not some massive server farm.
8 hours on a consumer GPU. That changes everything.
It really lowers the barrier. And crucially, it does all this without needing any robotic data pre-training on the VLM backbone itself. So how does it actually pull this off?
Well, the researchers did a very systematic analysis. They wanted to figure out how different kinds of perception information really influence action generation. They basically looked at two main types. First, raw features, the direct vision and language info straight from the VLM. And second, additional query features. These are like learnable queries specifically designed to act as bridges between perception and action.
Okay, so they're asking what specific bits of info does the robot need and from where in its brain, essentially, to make the right move.
That's a good way to put it. And their findings were quite interesting. For those raw latent features, the direct vision language stuff, they found middle layer latents worked better than the deep ones.
Middle layers. Not the deepest ones. Why is that? Well, it seems these middle layers are sort of the sweet spot for integrating image and text info. They retain a richer mix of multimodal details needed for action. The deep layers are great for high-level understanding, sure, but maybe a bit too abstract for the specific nuances of generating an action command. It's about actionable intelligence, not just abstract semantics.
That makes sense. Actionable, not just conceptual. Okay, what about the other type, the action query latent features? Same story there.
Interestingly, no. Completely the opposite, actually. For action query latents, the deeper layers performed better than the shallower ones.
Huh. Why the difference?
Because these action query features are trained from scratch, specifically as bridges. So the deeper layers do a better job of aggregating and refining all that multimodal information precisely to promote action generation. They're purpose-built for it.
Got it. So purpose-built features benefit from deeper processing. And VLA-Adapter doesn't just pick one or the other, right? It seems like it uses a mix.
Exactly. Their third key finding was that using multi-layer features, combining info from different VLM layers, generally beats relying on just a single layer. It boosts performance and makes the design more robust. And VLA-Adapter is clever about it. It doesn't just rely on action query features, it strategically pulls in specific knowledge from raw features too, especially when tasks get trickier. It's a kind of hybrid approach. So, this smarter way of handling information feeds into the VLA-Adapter's policy network. This is the part that actually decides the robot's actions. It uses an L1-based architecture. You can think of it as a simpler, maybe more direct design compared to some complex transformer setups. Experiments showed this choice gives better performance and, importantly, faster inference, especially during fine-tuning.
Simpler, faster, but still effective. Okay, so what information does this policy module look at moment to moment to make decisions?
Right, at each step, it gets quite a comprehensive picture. It takes in a third-view image for broad context, plus a gripper image for close-up detail. It also gets the instruction you gave it, those action query features we talked about, an initial action hint, and critically, the robot's proprioceptive state.
Proprioceptive state. That's like its internal sense of where its body parts are.
Exactly, like knowing where your arm is without looking. It gives the robot a full checklist, basically, all the context it needs for the next move. And the real magic, or well, the core mechanism for blending this is the bridge attention module. Think of it like a conductor, guiding how the raw features and the action query features are combined with the action information at that layer to shape the final action. It uses two cross-attention mechanisms, one for raw features, one for action query plus proprioception, and also a self-attention mechanism to weigh everything properly.
That sounds like a sophisticated way to integrate everything. I heard there's a particularly clever detail in how it balances these different streams.
Ah, yes. There's a really neat design choice, a learnable parameter they call ratio G. This parameter dynamically controls how much of the raw features get injected into the action decision process. It starts at 0 and uses a ton function to keep things stable during training.
So it learns how much raw perception is needed.
Kind of, yeah. But in contrast, the action query features, because they're already aggregated multimodal info, are fully injected. Their contribution is always set to 1, reinforcing their key role. It's a subtle but effective tuning knob. Now let's talk validation. The results are pretty convincing. For example, if you use a VLM backbone without any prior robotic pre-training, VLA-Adapter shows a really obvious improvement, like a 9.2% jump in success rate using a Qwen 2.5 0.5B backbone.
9.2% just from the adapter, without the backbone being pre-trained for robotics. That's significant. And what's really striking is that VLA-Adapter still works really well even if you freeze the VLM backbone entirely. It hit an 86.4% success rate then. How does that compare?
Well, under the same frozen conditions, Open VLA-OFT got 0.0% success, and Small VLA got 77.0%. So 86.4% is a huge win for VLA-Adapter.
Wow. So it can work powerfully without even needing to tweak the main VLM. That's a big deal for efficiency.
It really is. It highlights how effective that bridging paradigm is on its own. You see, other pre-trained VLMs adapt their last layers for action, but if the VLM isn't pre-trained that way, its last layers aren't enough. That's where VLA-Adapter's specific bridge becomes so crucial for effective fine-tuning.
And speed-wise, you mentioned it was fast.
Extremely fast, that 219.2 hertz throughput we mentioned. Compare that to Open VLA-OFT at 71.4 hertz or the original Open VLA at just 4.2 hertz.
4.2 hertz, that's slow.
Right. VLA-Adapter speed translates to incredibly low latency, about 0.0365 seconds per decision. That makes it super responsive for real applications. And looking at overall performance in simulations, on the big Libero benchmark, VLA-Adapter really stands out. It achieved an average success rate of 97.3% across a whole range of tasks, spatial, object goal, even long horizon ones. And this is with that tiny 0.5B parameter backbone.
97.3% with the small model. How does that stack up?
It's comparable to models using backbones 14 times larger, and it beats other leading methods like Pew, Small VLA, GR00, TN1. Notably, on the really tough Libero long tasks, it had a 29.0% advantage over VLA-OS, another model with the same small backbone size.
Okay, so it's not just efficient, it's genuinely top-tier performance. What about generalizing, handling new situations?
Good question. On the Calvin ABCD benchmark, which tests sequences of tasks, it showed strong generalization, high success rate completing sequences, and it managed an average of 4.42 tasks completed correctly in a row, outperforming other baselines.
So it learns patterns well.
And importantly, this isn't just simulation success. They did real-world robot tests, too. VLA-Adapter showed better generalization across various real tasks. Simple pick and place, yeah, but also tricky stuff like moving a block sideways carefully, stacking blocks precisely, and even complex long-horizon tasks like pick up the spoon, put it on the cup, then put the cup on the plate.
That multi-step task is impressive.
It really suggests VLA-Adapter significantly lowers the barrier for actually using VLA models in the real world on practical robots.
Okay, to really nail down why it works so well, the researchers did ablation studies, right? Picking apart the design.
Exactly. They tested key choices. For instance, the number of action query tokens. Too few, and the robot struggled to link perception and action. Too many, and it became redundant. They found the sweet spot was 64 tokens for the best balance of performance and efficiency. It's that kind of tuning.
Makes sense. And they also tested using just raw features versus just action query features.
Yep. And the results clearly showed that using both the all-layer raw features and the action query features, which is VLO-Adapter's hybrid approach, gave the best performance. A 95.0% success rate, better than either type alone. It validates that design. And finally, they looked at how features get injected into the policy network. The ablations confirmed that the bridge attention design works best, having that learnable ratio G for raw features, but fully injecting the action query features because they're already refined multimodal info. Each part of the design really seems justified by these tests.
Right. Now, despite all this success, it's important to be realistic. The researchers themselves point out some current limitations, don't they?
They do, absolutely. It's not perfect yet. First, generalization in really complex, varied real-world settings still needs improvement. That's partly because it's a small model and isn't pre-trained on those huge embodied data sets like some larger models are.
Okay, so real-world robustness is still a work in progress. What else?
Second, the quality of the action still depends quite heavily on the quality of the conditions, the information provided by the VLM, and how it's used. So there's more research needed there, exploring how to optimize those conditions even further.
I see. And a final point.
And finally, the training process itself is currently fairly straightforward, mainly imitation learning. They suggest exploring more complex methods, perhaps reinforcement learning, could potentially unlock even better performance down the line.
So, areas for future work definitely exist. But stepping back, we've seen how VLA-Adapter offers this really compelling new path for robotics. It's delivering state-of-the-art results while slashing the computational cost, the training time, and the reliance on giant models. This isn't just about faster robots. It's really about making advanced AI much more accessible.
It really is. You have to consider how this shift towards efficient, small-scale VLA models could change the landscape. Who gets to develop and deploy advanced robots now? If you can train genuinely powerful robotic intelligence in, say, 8 hours on a regular GPU, well, what kinds of new innovations and applications could you listening right now imagine? Things that maybe seemed out of reach before?